Hello everyone. Today we will be presenting a machine learning project focused on predictive modeling. The objective of this project is to predict whether the horse can survive. Based on a cargo competition dataset which contains medical records of horses, we'll be exploring various classifier and ensemble methods. Our top performing model ranked in the top 6.5% on the cargo leaderboard. We begin by performing exploratory data analysis. The full dataset consists of 2,059 entries. The dataset includes 29 variables ranging from physiological metrics like temperature and heart rate to subjective assessments such as pain level. Variables are categorized as numerical, binary, and categorical, with columns for unit identification and class labels. About 2.3% of the data has missing value. Numerical variables such as hospital number and total protein shows skill distribution, possibly linked to outcome. Lower hospital number tend to lead to outcome that the horse can survive. Binary variable shows imbalance, particularly in surgery, indicating higher surgery frequency. And we found a correlation between not undergoing surgery and higher survival rate. For categorical variable, lesion 2 and lesion 3 had many zero entries, possibly lacking meaningful information. And some variables seems to be correlated with positive outcome. During our feature correlation analysis, we found that many features having low positive correlation with the outcome variable, and some physiological measurement-related features show positive correlation with each other, indicating potential multicollinearity. Assessing feature importance, we identified that hospital number and lesion 1 as most important factor to outcome, while lesion 2 and lesion 3 were insignificant, suggesting that removing them might help to improve model performance. During pre-processing, missing values were addressed by mode imputation, filling them with the most frequent value in each column. Normalized numerical variable using min-max normalization to mitigate the influence of larger values. Binary variable were encoded with label encoding, while categorical variable use one-hot encoding for variable values which has a one versus rest nature, and label encoding for variable with ordinal values. Feature selection retains significant features, removing irrelevant ones like lesion 2 and lesion 3. Based on the dataset's characteristic and the multi-class classification problem, we selected a range of classifiers and explored their strengths, weaknesses, and performances. Additionally, we also explore ensemble method. For model performance assessment, we split the full dataset into train and test set, further dividing the training data into training and validation dataset. And we use 5-fold cross-validation approach to rotate different subsets as validation data to ensure robust performance assessment, particularly when facing unseen data. To optimize model performance, we use grid search for hyperparameter tuning, exhaustively explore all combination of predefined hyperparameters with cross-validation to fine-tune the models. We assess model performance using the F1 micro-average score, which balances precision and recall by considering true positive, false positive, and false negative across all classes. In this session, we will summarize our observation when exploring each classifier model and ensemble method. The support vector machine is chosen for its ability to handle datasets with non-linear relationships, matching our dataset's characteristic. SVM excels in high-dimensional space and multi-class classification tasks by identifying clear margin between categories, although it may struggle with high noise levels or overlapping classes. For hyperparameter tuning, we explore parameters like C and gamma and different kind of kernel method. The optimal SVM model results in an accuracy of 0.7 in the train set and 0.73 in the test set. The train accuracy refers to F1 micro-average score for train set, and the test accuracy refers to the published score on cargo after submitting the prediction on the test set. The K-nearest neighbor model is chosen for its simplicity and ease of implementation. Its lazy learning approach doesn't make assumptions on the data distribution, making it suitable for various tasks, but it may face performance issues with high-dimensional data and large dataset due to the high cost in calculating distance between each pair of data points. After hyperparameter tuning, the optimal KNN results in a train accuracy of 0.75 and a test accuracy of 0.75, indicating good generalization to unseen data. Moving on to the decision tree model, it is chosen for its interpretability, which is crucial for understanding the decision-making process behind predictions. However, DT are prone to overfitting, especially with deep trees or noisy datasets. The optimal DT achieved a trend accuracy of 0.68 and a test accuracy of 0.72. Lastly, the artificial neural network model was selected for its ability to capture complex patterns due to its multi-layer neuron structure, and it also offers flexibility in training and optimization algorithms. However, the black box nature of it poses challenges in interpreting predictions, and they typically require greater computational resources. After hyperparameter tuning, our ANN achieved a trend accuracy of 0.67 and a test accuracy of 0.65, slightly lower than other classifiers. In our exploration of ensemble method, we began with bagging, which reduces variance by training multiple learners on different data subsets and averaging their predictions. It enhances stability and generalization, but it may not effectively address bias or underfitting. Our optimal bagging model achieved a moderate training accuracy of 0.49 and a test accuracy of 0.46, even worse as compared to single classifier due to underfitting. Next is random forest, which combine multiple decision trees to enhance generalization, mitigate overfitting. Each subtree trained on different data subsets with random selection of feature subsets. However, RF's complexity and reduced interpretability poses challenges. The optimal RF model achieved a strong performance with a trend accuracy of 0.99 and a test accuracy of 0.77. Next will be stacking, which enhances accuracy by using results from multiple models as input data to a meta-learner for training. However, stacking introduces complexity and longer computational time. The effectiveness of stacking depends on the diversity of base model. Less correlated model will have better performance. Our optimal stacking model achieved a trend accuracy of 1 and a test accuracy of 0.78. AdaBoost is chosen for its iterative training approach, progressively improve weak learners by focusing on misclassified instances. Through weighted aggregation, it is useful to prevent overfitting, and it requires minimal hyperparameter tuning. However, AdaBoost effectiveness depends on quality training data. It is highly sensitive to noise and outliers, and the efficiency of base learners. The optimal AdaBoost model achieved a trend accuracy of 0.75 and a test accuracy of 0.76. Light gradient boosting is to progressively improve weak learners in a gradient descent manner to minimize bias error and enhance accuracy. However, its vulnerability to overfitting due to leaf-wise splitting and hyperparameter sensitivity can pose challenges in tuning, potentially require extensive computational resources. The optimal LGB model achieved remarkable trend and test accuracy of 0.93 and 0.81, which shows that it generalized well to unseen data. Extreme gradient boosting, or XGBoost, which is also based on gradient boosting framework, stand out for its strong capability and wide range of hyperparameters. However, its complexity in hyperparameter tuning demands substantial computational resources. The optimal XGB model achieved trend accuracy of 1 and high test accuracy of 0.81, shows that it performs well on unseen data. And the last one, which is histogram-based gradient boosting. It is also a gradient boosting algorithm. By using histogram-based method, group feature values into bins, leading to faster training and lower memory usage. Its memory efficiency and speed are crucial when resources are limited. During optimization, hyperparameters like maximum depth, maximum iterations, learning rate, maximum leaf nodes, and L2 regularization were fine-tuned. The best HGB model achieved a trend accuracy of 0.94 and a test accuracy of 0.84, which is the top performer among all methods, and secured the position of top 6.5% on the Kaggle competition leaderboard. This is a performance summary of all models. Out of all the single classifier, K-nearest neighbor and support vector machine performed well, followed by decision tree. Among all the ensemble method, histogram-based gradient boosting performed the best with a test accuracy of 0.848, followed closely by light gradient boosting and extreme gradient boosting. Overall, ensemble method surpassed single classifier. Besides performance, we will also need to consider other factors. Ensemble methods are effective in capturing complex patterns, but it can overfit, achieve higher accuracy in trend set, but lower in test set. Interpretability is crucial for certain scenarios like in banking. Single classifier like decision tree are easier to understand, while ensemble methods like gradient boosting or stacking can be harder to understand the decision-making process due to the ensemble nature. Computational complexity is also a factor to consider. In conclusion, histogram-based gradient boosting emerged as the top-performing model, demonstrating excellent accuracy and reliability, and generalized well on unseen data and manageable computational cost, strike a balance between performance and other factors. Despite sacrificing some interpretability, its exceptional predictive power make it the preferred choice for this project. Thank you for watching this video.